Hey everyone, and welcome to The Explainer. Today, we're popping the hood on the power grid. From an engineering perspective, we're going to dive right into how data, AI, and green energy are colliding to solve a massive, almost totally invisible problem lurking inside our modern electrical networks.
Now, we all know electric vehicles are the future, right? But here's the thing. They introduced this massive hidden monster into our local grids. When owners charge up at home without a dedicated EV meter, those huge power draws just blend right in with normal household usage. It creates this wild, unpredictable strain that can literally overload local transformers. So how do we as engineers actually hunt down these invisible monsters?
Core problem we face is a major lack of labeled data. Finding an EV charging session is kind of like finding a needle in a haystack of everyday appliances. But instead of forcing an AI to read endless, mind-numbing rows of raw numbers, engineers use a really clever visual hack. If you look at the power draw, a typical EV charging event creates a super stable, blocky plateau because it's just drawing high power constantly. But compare that to normal domestic use. It's full of random, chaotic spikes. It honestly looks like a messy heartbeat monitor.
Mechanically, the data transformation is actually a pretty brilliant, simple process. You've got smart meters collecting aggregate active power data every 30 minutes. Engineers take that time series data and just map it directly onto a graph. The x-axis is time, and the y-axis is the power level. And just like that, these messy power behaviors transform into unique, recognizable graphical fingerprints.
To actually analyze these brand new images, we rely on deep transfer learning. Think of it like this. Imagine a master pianist who decides to learn the guitar. They don't have to relearn what rhythm or notes are, right? They just transfer their existing musical foundation and pick it up incredibly fast. We're essentially doing the exact same thing. We let our AI stand on the shoulders of giants.
We take a veteran, pre-trained AI model, one that's already spent thousands of hours grinding through the ImageNet database, mastering how to identify edges, shapes, everyday objects, you name it. Then we tweak it just a little bit and feed it our new EV load fingerprints instead.
Here is the actual engineering blueprint. First, we literally freeze almost all the pre-trained layers of the neural network. This locks in its existing visual recognition skills and, crucially, saves a massive amount of computing power. Next, we bolt on a brand new, fully connected layer with exactly 256 neurons to act as our new decision maker. We input our smart meter images, and the model spits out a simple binary output. Yes or no? Is there hidden EV charging happening here?
And the results? Well, when tested on completely unseen data, the EfficientNet V2B1 model didn't just work. It absolutely crushed it with a stunning 93.45% accuracy rate. It successfully plucked these hidden charging events right out of a total ocean of noise.
To put that into perspective, when you stack this up against traditional baseline models like LSTM or TabNet that are just chewing on raw numerical data, their accuracy hovers around 87 to 89%. But by converting the data to images and applying that deep transfer learning, EfficientNet V2B1 just dominates across every single metric. But look, any engineer will tell you that raw accuracy isn't the whole story. False alarms are expensive. That's why the F1 score of 93.42% is absolutely critical here. It proves the model has an exceptional balance between precision and recall. I highly recommend checking out their full paper if you want to take a deeper dive into the exact neural network architecture.
Thanks so much for joining me for this explainer, and I'll catch you next time.